Hello there. Oh, I know this simple explanation has been taking a long time. That time has been very well spent building this little program that I would not have needed to explain the concept of these curves, but I wanted to have a program like this, and it was a lot of fun to get it to this stage at least. There's a lot more I can do. There are numerous bugs, but most of them have some kind of workaround, so I can usually get it back into a state that's usable if something bad happens. I thought I had silenced the assert messages, but they're still coming up. See now, I don't think there's anything else I can do to turn them off. I've probably broken that. I did a lot of reorganizing in this, so this doesn't do anything. In this area, see, it used to be that, clean this one up too. There was just something called, something like this, something like TS common. I think it's a common. I guess it was kind of similar, and then it lists everything by program name. And this is the program. Oh, it was called CRT debug, and there was a program name. But now I figured there might be other things too that are in this common area besides this bunch of flags. And is there anything else? Well, there are some things I want to add. Like one of the things that would be a good flag that you could set, maybe, would be allow only one instance of the program or something like that. Anyway, so now some of this is kind of mathy, and I was thinking that for instance, like these Legendre polynomials, these are a subset of a particular order of these Legendre polynomial things. Let's see, how shall I say it? Okay, I'm going to give you a very quick, I can use my program for this too. A very quick intro into linear algebra. Let me just I'll make it big. Now, it's very easy for us to understand something like this two-dimensional Cartesian coordinate system, where we have the point, and I make these a little bit bigger. I don't know if that's more visible. Okay, and does this work in here? Yes, it does. It has a position x, y. let's give it a name, P. I think I can fix this. It won't accept the keyboard, but I'm pretty sure I know why. Actually, I don't want that one. Well, it's okay, I can still fix it. And I can still just add a... Oh, I forgot. Where is the little sign? There it is. Okay, P equals xy at some point in the xy plane. This being x. Fix that. This is the x-axis, and this here enter. The y-axis. Alright, so now we can write any point uniquely in the coordinate plane by specifying two numbers. And that's one of the reasons why you would call this space two-dimensional, because it requires two numbers to uniquely specify a point. And you can prove that it is a unique specification. Now what I want is this mode. Just to draw. So this is those are the which is thinner now. the coordinates are obtained by just this here is the height y, right, and this is this distance here is x. Oops. It looks better now. Enter. Right? That's very simple to understand. And now these coordinate axes, these perpendicular axes, in linear algebra form what they call a basis for this space. That is, these axes are actually vectors, or represented by vectors anyway, in two space, and every position in the space can be written as a combination of those two, some linear combination of those two vectors. Usually like the engineers or something, they'll write the vectors that specify or that describe a space in terms of unit vectors. Like for instance, there's this Hamilton, what they call quaternions, invented by Hamilton. I don't know if he's in my stamp collection. I don't know how to write it, but it has to be I with a little hat on top. I probably have one in my special characters. But anyway, imagine it's this I with a little hat on top, okay? It's a vector. And it's parallel to the x-axis. And then there's another one called J. Actually, the engineers don't use I and J. They use different letters. They use they don't want to use I, which is understandable. Oh no, they use I and J. That's right. What they don't use is I for the square root of -1. They use J for that. I know how to fix this problem. That there is a modeless dialog box, I'm pretty sure. And so I have to add its h-wind to my, if I add its h-wind to my modeless list, it'll handle the keyboard. Okay, so this J thing, and these are both unit vectors. So any vector in the plane, so take any vector, and it's barely fits, doesn't it? I don't know if I can delete the last thing. Put it on this. Doesn't matter. Okay. You can come out of it. And you can always write it as so we'll take any point, doesn't not even vector, any position as say P equals some constant value, like a numerical scalar value, A, oh, where's my little dot thing? Can't do that now. Anyway, AI, right, like that, make it obvious. And then another scalar value, like that. So this is what they call a linear combination of these two vectors, right? And you can write any vector in the plane in this form. And if it so happens that I and j are unit vectors, then a and b are simply x and y. So we have p equals x times I plus y times j. So that makes it very convenient in the unit vectors, because then the scalar quantities are just the coordinates. Okay. Now, One of the things that about these i's and j's are they don't have to be unit vectors. It could be w and z or whatever labels you want to give them. Are not unique in the sense of being able to describe this coordinate plane. You could form another set of vectors or lines. How about I draw lines with a different color? We could jazz this up a bit. How about orange? And one. How about like this? I can still do it. I can cover a little. I don't want them the same color. Almost made it. Okay. Now these you might call the u-axis. And this might be the v-axis. Now if these axes are not parallel, then they also form a set of vectors that describes this entire plane. That is, you can always write the same point P. I won't type it in, type the description, I'll just write it. Equals, but I'm going to do it in a special way. Now, they won't be the same scalar quantities, but I'll call them x prime, say. These might be based on some other unit vectors. I'll put this in order. Come on. There's so many things now, it's slowing down. Okay. So we can write the same vector in the new coordinate system in this way. Okay. Now that can be proved. That can be proved that that it is possible, provided that these two vectors are what they call linearly independent. Okay. Now in the xy plane, that just means that they're not parallel. Parallel lines would not be linearly independent. You could write, you can find an expression that relates the two coordinate axes so that one, like v, if v can be written in terms of u, then I could substitute that in here, and this would only be a function of one variable, and then we wouldn't be able to describe every point. Now that same point in terms of u and v, right? How would we determine those? Well, if it's going to be something like this, and if these are unit vectors like along these axes, it's going to be a linear combination of u plus v, right? Now, how would I get there? I would say I would have, if I wanted to get there, I have to use a different color. to get to P, I draw a line, actually, it's a line parallel to, I'm going to draw a line parallel to V. I don't want this mode. I want line. How about it? Well, it should be orange, but I don't want it to be exactly the same. If I draw a line parallel to V from here, maybe like here to here, right? And then another line from here to here, which you can't see. Well, now you can see it. Then the sum of these two vectors, I'm not going to use this magic vector thing. I'm going to put it in back in, oh, how about red? No, so you can see. Oh, they're appearing underneath, I see, too bad. But you can sort of make it out. You can see that if I add this vector to this vector, I get the same point P. And that's how you construct a position using these two axes. Now, why am I talking about this? Because this is something that's very easy to understand in terms of coordinate planes and vectors and adding vectors and straight lines and so on. It turns out that the same idea can be applied to functions. Like any function, it turns out, well, certain class of functions, like continuous functions and whatever. Any continuous and infinitely differentiable function, it so happens, can be written as a polynomial of infinite order. And that's called Taylor's theorem. And I wrote it down, in fact, and mailed it to myself. And this is the way, this is how it works. First part. This thing is called Taylor's formula, and the bottom part is one result of that. Okay, there are two kinds of ways of writing a function in terms of polynomials. In this math, there are a whole variety besides these two. If you're just writing a thing, if you just want to write a function as a polynomial, first, it is possible to prove this thing. That suppose f is that should be an f, but whatever, is some function, and n is some positive number, and z here, which is different from a, is somewhere within. Actually, these should be round brackets, I think. Should it be? Maybe not. Maybe square. There is a number. Actually, I think it has to be round. Yeah, it has to be round. I think. No, not necessarily. Because if the thing that you're working on, happens to be a polynomial in itself, then this thing could terminate, and you might already have the answer. Not important. The point is that what you do is to get f of b from f of a, you write f of a, and then you take its derivative and multiply by the difference of the range, b minus a. Then you take its second derivative and divide by 2 factorial and multiply by b minus a squared, and so on and so forth in exactly the same manner until you get to some number n you've already decided on, like 100, let's say. The 100th derivative of f at a over 100 factorial times b minus a to the 100, and then plus one extra term called the remainder, and you can show that this remainder gets smaller and smaller and smaller as you increase the value of n. In particular, if a happens to be 0, okay, if it's possible, sometimes you can't, sometimes a is not valuable as 0, like log x wouldn't be, you couldn't use 0 for, if you wanted to express log x in this manner. You can express log x in this manner, you just can't use 0 for a. But if you can use 0, then you get what's called the Taylor series form of a function, which looks like this. F of x is f of 0 plus f prime of 0 x plus double prime over 4 times x squared, and so on and so forth. And you get a polynomial. And I just worked out quickly the first few terms for cosine of x. You take cos x, and here are its first 4 derivatives, and its first 4 derivatives. Cos derivative is minus sine, and the derivative of that is minus cos, and then that brings you back to sine, and then cos again, right? So in terms of these numbers here, f of 0 is 1, so the first term is 1. F prime of 0 is 0, so there's no linear component to it, right? Then the next term is minus 1, and that's for the quadratic term, and so we get minus x squared over 2. The next one is 0, and the fourth one gives positive. So in fact, this sign alternates plus and minus as you go on. The next term will be x to the 6 over 6 factorial. It's very simple, really. And in particular, the simplest one really to remember is e to the x. E to the x. Because e to the x is equal to its own derivative, all of the leading terms are the same. It's always 1. So that gives you 1 plus x plus x squared fraction 2 factorial, that is 2, then the next one is x cubed over 3 factorial And then you see it's really quite easy to remember. Even after, you'll see it even better when I press F8. Next. Oops, I've got to add a dot dot dot. Come on. Oops, plus dot dot dot. And it just goes on and on like that forever. Okay? So just 1, 2, 3, 4, and so on. And that gives you e to the x. Now one of the things you'll notice about this is that if I take the derivative of e to the x, written this way, what do I get? What was that derivative thing? Yeah. It has a handy derivative. That's partial. Oh, here, this one. Oops. D e to the x by dx. Is that right? Equals minus square d by dx, and then this whole thing more copy. Copy. Well, that's going to wrap around. We'll see. Oh, that's okay. Alright. So the derivative of e to the x with respect to x is that. So that gives you can guess the answer. It's supposed to give itself back again, right? Derivative of 1 gives you 0, plus, and then the derivative of x with respect to x gives you 1, and then x squared over 2 factorial gives you 2x. Now 2 factorial is 2, it turns out, plus, and then now we get 3x, what is that, c dot, squared over, now 3 fact, I'm just going to write this one out. 3 times 2 times 1. Just so you can see it explicitly why it works. 1 more. The next one will be 4 . x cubed divided by 4. I have my own dot faster than this one. That works. Okay, it's the bracketing front. But you can see that's 1 equals 1 plus x plus. Now the 3 cancels with this first 3 in the 3 factorial, so we end up with 2 factorial. In the cubed case, the 4 case, sorry, these 4 cancel, and so we have x cubed over 3 factorial. Okay. Which is equal to e to the x. If we defined e to the x this way to begin with, then its derivative with respect to x would retrieve itself. And in fact, most functions that people in science work with are defined mainly in terms of their power series, and not these special names that have special meaning. And so that makes life a lot easier to deal with, because you're always just dealing with polynomials. And polynomials, it turns out, were the hardest one on my graphing thing to really get a grip on drawing, because they tend to zip away very quickly, and it's hard to adjust, the multipliers and scaling and so on, so that they look good. Now, in particular, I can send that to myself. Now, this x squared, x cubed, x to the 4, and 1, okay, which is just a constant. Not completely. Well, yes, completely. Form what they call a basis for the set of continuous functions of x. Functions f of x, y equals f of x. And these things are analogous to the vectors that I was showing you before for determining a point. These are like vectors, okay, that determine a function. The analog of this is going on a long time, right? Anyway, this will be another playlist too. The analog in mathematics, in linear algebra, for vectors in space, like with arrow lines and arrows, like coordinate systems. For functions, are sets of functions which have the property of being linearly independent, okay, and that can uniquely describe any point, and the point, the analog of point is a function, okay, like e to the x, in the set of continuous functions. So there's a symbol for that. I think it's a big C with a second line to it or something. They have that symbol here somewhere in set theory here. This thing, this C, is the symbol, I believe, that represents the set of all continuous continuous differential and differentiable functions of x. It's not the only set of functions in the world. Some functions can't be differentiated, and so there are various other sets. But this set has at least one basis set that you saw. Just the powers of x are linearly independent vectors, quote unquote, in that space, and any function can be written as a linear combination that is a constant number times one of those vector values in some combination, and that one way is with x squared, x cubed, and so on. But it turns out that it's often more convenient not to use x and x squared and x cubed, but to use combinations of them. The solutions that describe certain certain types of functions are more conveniently written in terms of polynomials that are not just x and x squared and so on. An example of that are the Hermite polynomials, and the ones that we're looking at are not the Hermite polynomials. They're just a couple of them at the third order level. And there are various forms even of the Hermite polynomials. But they show up in physics and mathematics all over the place. A very important set of functions. Another set is the Legendre polynomials. Those ones show up in quantum mechanics. I don't know if you've ever heard of something called a quantum number, okay? But it turns out that the solution to the main equation in quantum mechanics, Schrodinger's equation, those solutions are most conveniently written in terms of these Legendre polynomials, but not of distance of some, common another something else, like it would be usually in polar form, and it's like a combination of cosine and radius and various things. But those bases, the basis set that's written, for instance, that's most convenient to describe an atom, okay, are written in terms of those Legendre polynomials. I think it's Legendre polynomials. And the quantum numbers that you hear about correspond to the various polynomials that are used to describe the state of a particular system. Just a little bit of trivia. So now you've had quick introduction into the theory of linear algebra as applied to continuous functions, and the Hermite polynomials are an example of such functions. And just a couple of those polynomials, it turns out, can be used to describe a line between 2 points that has the property of being tangent, where you specify the tangent vector at one point, and at another point you can write the curve down in terms of those polynomials. I can show you what they look like. And it turns out that writing that solution for the continuous function is unique. There's no other solution at the third order. Okay, I mean, we're talking about if it's going to be a cubic, there's only, now here I made them big, I scaled it by 200. Okay, these are the 4 ones that are used. H1, 2, 3, and 4 are what they call them. This is really only going from 0 to 1, but this is scaled by a factor of 200. So this is 1, and this is 1. So these 4 functions can be used to describe the motion or path that something might move through in a continuous way with cubic, with the property of being a cubic form. The higher the degree, the more possibilities there are. But as far as for cubic, there's only one solution for any given points and their tangent. And it's given, well, I'll show you what it's given by next time. And I'll show you why it works and how it works and why this is very easy to understand. It might look complicated by staring at these 4 graphs. What these graphs represent, okay, are the t values for the parametric form of a point in space, and we've studied that. If you understand the parametric form of a straight line, then you'll see how this works. Okay, that's too much, and this will also be part of my, I don't know, mathematics reference playlist too. Okay, see you.